Tiled multi-projector displays provide seamless large area visualization for a wide variety of high-resolution applications. Traditionally, multi-projector systems have used a centralized architecture where a single server is responsible for managing calibration and projector content. Our starting point is a distributed architecture for building tiled displays using a network of plug-and-play projectors, or PPPs. Each PPP consists of a projector, a camera, and a communication and computation unit simulated by a network PC. Our prototype display consists of 9 PPPs in a rear projection configuration. In Bhaskar et al.'s work, a blob pattern is used to discover a PPP's neighbors. Then, through multiple rounds of information exchange through binary-coded blob patterns, each PPP discovers the configuration of the display, as well as its position in the display in logarithmic time. Finally, the blobs used in the neighbor detection phase are also used for registering the PPPs using a distributed homography tree technique. However, distributed homography trees can result in large misalignment due to accumulated errors. Camera-based communication is also computationally intensive and slow to converge on large displays. In this paper, we first propose a new distributed registration algorithm that improves accuracy and efficiency significantly. We then introduced the first distributed paradigm for interaction with rear-projected large-area tiled displays that scales to multiple users, applications, and interaction modalities such as touch and laser pointers. For distributed registration, we propose using QR codes augmented with Gaussian blobs. Each PPP displays a pattern of 4 augmented QR codes. Then its camera sees the QR codes of itself and all of its neighbors. We highlight the PPP's own QR codes, as well as those of its top, right, bottom, and left neighbors in the camera view. By processing the QR codes of the adjacent PPPs, we can simultaneously achieve neighbor detection, configuration identification, and registration. Finally, we present a novel, radially cascading distributed geometric registration algorithm that achieves greater accuracy than the distributed homography tree or a global optimization technique. To demonstrate our distributed interaction paradigm, we use 2D gesture-based interaction. Each PPP is augmented with an infrared illuminator and a removable visible light cup filter. When a user touches the screen, infrared light is transmitted through the screen and reflected off of the user's hand to the camera. During calibration, the visible light filters are removed and then put back to resume interaction. We consider interaction to be a set of 2 consecutive events: a 2D gesture performed by the user and a consequent reaction provided by the display. Since gestures can occur over an extended period of time, they can span multiple PPPs, moving across them. Furthermore, a reaction may need to occur in a PPP that the user did not directly interact with. For example, when moving a large map, a gesture may span only a few PPPs, but all the PPPs must react. Our interaction paradigm is comprised of an SPMD algorithm running on every PPP. This algorithm has 2 components that run concurrently: distributed gesture management and distributed reaction management. These work in a producer-consumer relationship, where the former produces gestures for the latter to consume. To demonstrate the scalability of our distributed interaction paradigm, we created 4 multi-user interactive applications. A graffiti application allows multiple users to collaboratively paint on a canvas spanning the entire display. Users choose colors from a palette and vary their stroke width based on their contact area. To demonstrate the ease of interaction, we brought children ranging from ages 7 to 13 years old to draw on the display in a collaborative manner. It took them only a few minutes to get comfortable interacting with the display, and its inherent scalability allowed multiple children to simultaneously draw on the screen without introducing additional latency. Our map application allows users to interact with the map that spans the entire display. As well as define personal windows that they can interact with without disturbing the full screen map. Users can pan, zoom, and choose from different map layers like a relief or a road map. We also developed an emergency management application where we simulate a command and control center where multiple co-located personnel can define hazard locations, dispatch units to different areas on the map, and mark the routes for the units to take. This information is relayed to the ground, and the visualization is updated to reflect the current state of the situation. Finally, we demonstrate a virtual bulletin board where users can post notes and flyers and manipulate them by moving, scaling, and highlighting. Multiple users can simultaneously add and change the state of the display independently. To demonstrate the scalability of our paradigm to different interaction modalities, we also show multi-user interaction with blue and green laser pointers with our existing interactive applications. In summary, we have presented a new distributed geometric auto-calibration method for tiled displays. Our method more accurately registers distributed multi-projector displays, making it amenable to natural multi-user interaction. We then presented the first distributed paradigm for interaction with tiled displays that scales not only to the number of tiles, but also to the number of users, applications, and interaction modalities.